Have you ever popped a painkiller and just wondered, what happens next? You swallow a pill, your headache vanishes, but where does the medicine actually go? How does your body know, okay, job's done, time to get this stuff out of here? Well, it's not magic. It's this incredibly complex, microscopic cleanup crew that's working inside you 24/7. And today, we're going to pull back the curtain and see how it all works.
So here's our game plan. First, we'll meet these unwanted guests, all the foreign chemicals our bodies have to deal with. Then, we're diving straight into phase 1 metabolism, which is the crucial first step. We're going to open up the chemical toolkit our body uses, introduce you to the master enzyme that runs the whole show, and then we'll look at the huge real-world ripple effects all of this can have.
All right, first things first, we need to get a handle on what our body is actually up against. From the medicine you take to things in our food and environment, our bodies are constantly bumping into foreign chemicals. And there's a sciencey term for all of this stuff: xenobiotics. But seriously, think about it for a second. For any drug to be useful, its effects have to be temporary, right? You need that painkiller to do its job and then politely show itself out. If it just stuck around forever, it would go from being a lifesaver to, well, a toxin. So how does the body hand it an eviction notice? The answer is this absolutely brilliant detoxification system. This whole cleanup mission is called biotransformation. It's basically your body's way of grabbing a foreign chemical and changing its chemical structure to make it easier to get rid of. And the undisputed command center for this whole operation, that's the liver. It is packed with all the specialized enzymes it needs to get the job done. Okay, so here is the central challenge your body has to solve. Most drugs, by design, are what we call lipophilic, or fat-soluble. It helps them get absorbed and get to where they need to go. But that also means they love to just hang out in the body's fatty tissues. They're like that house guest who just won't leave. To flush them out, the body has to make them hydrophilic, or water-soluble. And let's be clear, this isn't just about being tidy. This is about survival. If these fat-loving drugs aren't metabolized, they build up. Their effects accumulate, and what started as something helpful can become dangerous. So, biotransformation is, without a doubt, one of our body's most essential defense mechanisms. And that brings us to the first major stage of the cleanup, phase I metabolism. You can think of this as all the prep work. Before you can really get rid of that stubborn house guest, you got to get them ready to leave. That's exactly what phase I is all about. The mission here is crystal clear. Take that fat-soluble drug molecule and make it more polar. See, polarity is what helps things dissolve in water. So by making the drug more polar, the body is basically slapping a big get-ready-for-removal sticker on it, making it way easier for the next systems to spot it and flush it out. So how does it do that? Well, it uses these clever little reactions called functionalizing reactions. It's like the body adds a chemical handle to the drug molecule. It either uncovers a polar group that was already there, or it just bolts on a brand new one. For instance, adding an oxygen and a hydrogen atom, that's a hydroxyl group, is like attaching a little flag that says, "I love water." Now, this new handle might not make the drug fully water-soluble right away, but it creates the perfect spot for the next set of enzymes in phase 2 to come in and finish the job. So yeah, the main job of phase 1 is really to set the stage for phase 2. And this isn't the work of just one enzyme. Oh no. The liver uses a whole mixed function enzyme system. Think of it like a specialized assembly line with all these different protein workers, each one with a very specific job to do on that drug molecule. All right, so we've covered the what of phase 1. Now let's get into the how. Your body has this toolkit of chemical reactions that it uses to stick those handles onto the drug molecules. These are the workhorses that make the whole thing possible. The three main tools in this phase 1 toolkit are oxidation, reduction, and hydrolysis. Now, I know these might sound like they're straight out of a chemistry textbook, but they are fundamental actions that your body is doing all the time. Let's break them down. First up, and by far the MVP of the team, is oxidation. This is the body's go-to move for dealing with foreign stuff. It's the real powerhouse of phase 1, handling the vast majority of the drugs we take. So what is oxidation really? Well, at its core, it often involves using the oxygen we breathe to add one of those water-loving hydroxyl groups onto a drug. Let's take caffeine, for example. We all know caffeine, right? The reason your morning coffee works is because the caffeine molecule fits perfectly into certain receptors in your brain. To get rid of it, your body's enzymes use oxidation to add oxygen atoms, changing its shape. It doesn't fit in those receptors anymore, and that's why the buzz wears off. That one little chemical tweak starts to deactivate it, and, just as important, makes it more water-soluble. Our second tool is reduction, and it's basically the chemical opposite of oxidation. Instead of adding oxygen, it often involves adding hydrogen. It's less common for sure, but it's absolutely essential for certain types of drugs. For example, the anti-anxiety drug nitrazepam has a specific part of its structure called a nitro group. Through reduction, enzymes in the body swap that out for an amino group. This one little change is enough to deactivate the drug and get it ready for excretion. It's just another specialized tool for when oxidation isn't the right one for the job. And our third major tool is hydrolysis. The name kind of gives it away. You've got hydro for water and lysis, which means to split. So yeah, this is literally the process of using water to break a molecule apart. It's an incredibly elegant and simple strategy.
Now, check this out because this is where it gets really interesting. Sometimes phase I reactions don't just deactivate a drug, sometimes they activate it. This is exactly what happens with hydrolysis and a drug we all know, aspirin. Aspirin is what's called a prodrug. In the bottle, it's not very active, but once it's in your body, enzymes use a water molecule like a tiny pair of scissors. They snip off a piece of the aspirin molecule, turning it into its active form, salicylic acid. That's the stuff that actually fights pain and inflammation. So in this case, hydrolysis is both the on switch and the first step in getting the drug ready for removal later. A brilliant 2-for-1 deal.
Just think about that for a second. The most common molecule in our entire body, good old H2O, is a key weapon in our defense system, actively splitting chemicals apart. It's just an amazing piece of biological design. So we've seen the tools, oxidation, reduction, hydrolysis, but who's actually wielding these tools? Well, when it comes to the all-important oxidation reactions, there is one superstar family of enzymes that absolutely runs the show. So if you were to ask what the single most critical component in this entire system is, the absolute MVP of phase 1 drug metabolism, it would have to be this group of enzymes. The cytochrome P450 family, or what everybody calls them, the CYP enzymes. And this isn't just one single enzyme. It's a huge, massive superfamily of proteins. And when it comes to breaking down drugs, they are the undisputed champions. They're responsible for metabolizing the vast majority of medicines out there today. These enzymes are just incredible. They are ancient. You find them in almost every form of life, from bacteria all the way to us. In our bodies, they're concentrated in our liver cells, in a little factory area called the endoplasmic reticulum. And it's not just one type of CYP enzyme either. There are dozens of different versions or isoforms, and each one specializes in different kinds of molecules. And to do their work, they need oxygen, and they need a power source, which comes from a little helper molecule called NADPH. Okay, we have been way down in the microscopic details. Now let's zoom all the way out and talk about why this actually matters in the real world. Because the efficiency of this cleanup crew can be changed, and when that happens, the consequences can be huge. This brings us to a really important idea: enzyme induction. This is when taking one drug actually tells your body to start producing more of a specific enzyme. The drug is essentially telling your liver, hey, we've got a lot coming through. You need to build more of these cleanup machines, and you need to do it now. And this is where things get serious. Let's take an antibiotic called rifampicin. It's a well-known inducer of certain CYP enzymes. It makes the liver produce more of them. But here's the problem. Those supercharged CYP enzymes don't just work on the antibiotic. They'll speed up the metabolism of everything they're responsible for, including other drugs, like oral contraceptives. Let's just walk through this chain reaction, because it's so important. First, you take a drug that's an inducer. Second, it causes enzyme induction, and the liver's CYP450 system goes into overdrive. Third, this new supercharged system starts breaking down other drugs that are also in your system. And the result? That second drug gets cleared out of the body so fast that it doesn't have time to do its job, which can make it completely ineffective. It's a perfect example of a drug-drug interaction, and it's all happening right here at the level of phase 1 metabolism. So we've gone from a simple pill all the way down to the individual enzymes that clear it from our body. We've seen how this amazing system works and how it can be sped up or slowed down. Which really brings us to a final fascinating question. If we all have slightly different versions of these critical CYP enzymes, what does that mean for the future of medicine? Understanding this whole process isn't just a cool science lesson.
It's the key to one day tailoring drugs specifically to each person, making sure that they're both safe and effective for you.